Hi, this video is on chapter 6, section 1. We're working in the normal distribution. So I just want to quickly review what a distribution is. So a distribution is any way of communicating what values a variable takes on and how often or how likely the variable is to take on those values. All right, so I'm going to share my screen. I'm looking here at notes from chapter 4. Okay, so we have certainly been able to find values that a variable takes on and how frequently it takes it on using all of these techniques, frequency distribution, relative frequency distributions, histograms, relative frequency histograms. So I'm going to just kind of work with the histogram idea for right now as we go forward and talk about the normal distribution. So here are some histograms of 3 different distributional shapes. Shape is a significant component of the distribution. So of describing a distribution, and shape is also significant for deciding what inferential techniques are appropriate for the data that you're looking at. So knowing the distribution actually changes your choices and your options in analysis. And that's why we spend time on it. But it is the case that the normal distribution, the bell-shaped distribution, has the highest utility. So the normal distribution, the utility of this distribution exceeds that of all other distributions. Okay, so notice here that we have this nice bell and it's centered at 0. And this is what we call a standard normal because the mean is 0 and the standard deviation is 3. And we can confirm that because by the empirical rule, we know that the distribution, that a bell-shaped distribution has almost all of its observations within 3 standard deviations of the mean. So here's the mean of 0, and if I walk over 3 standard deviations, which would be when sigma is 1, 1, 2, 3 would bring us over here to 3, almost all my observations are within -3 and 3, and that is the picture that we see on the histogram. Here's a nice smooth curve of the normal distributional shape. All right, and a variable is said to have a normal distribution if the shape of the curve is normal. So if it looks like that. Okay, sometimes we have approximately normal or roughly normal distributions. And that would be the case where it almost looks like that. It almost looks like this. Okay, that's probably more common. So the normal distribution has 2 parameters. It has a mean mu and a standard deviation sigma. So here we are. In this case, the mean is 0 and the standard deviation is 3, which we can see because we note that the curve hugs the x-axis to the left of -3 and to the right of +3. Okay, so we have a few more curves here that are worth chatting about a little bit. The green curve has a mean of -2 and a standard deviation of 1. So if I count over 3 in each direction, that green curve should be up against the horizontal axis, and it is. Okay, and so we go to -5, and it is. And if we go up 1, 2, 3, -1, then that's where that green curve starts to level out with the horizontal axis. Okay. The red curve has a standard deviation of 1/2. So the mean is at 3, that's the high point, and 3 sigma, 3 times 1/2 is 1.5. So if we count over 1.5 to 4.5, then the curve is going to be up against the x-axis. So that's how normal distributions change. They only have 2 parameters. You can change their location with the mean moving around, then you can change how fat they are by changing the standard deviation. All right. So what we see is that for each normal curve, and each normal curve is bell-shaped, is centered at 0 and is close to the x-axis outside the range mu -3 sigma to mu +3 sigma. All right. So if we look at these graphs here, This is not, by the way, a question that will come up on a quiz, but I just thought it might be a little fun just to look at this. So looking here at this curve, what we want to do is we want to guess mean, and we also want to guess standard deviation. All right. So we see that the high point of this curve on the left is 10. So that lets me think that the mean is 10. But how am I going to get the standard deviation? Well, I know that for a normal distribution, the distribution, the curve hugs the x-axis once you get to 3 sigma away from the mean. So if I look, I'm going to just switch up the camera for a minute here. Okay. So we guess here that the mean is 10 and that we see this curve hugs the x-axis at about 15. So the distance between 15 and 10, which is 5, is representing 3 sigma. So 3 sigma equals 5. And to solve for sigma, just divide both sides by 3. Again, not something you need to do on your tests, but I just wanted to make sure I showed you that. You can start to build a little intuition about how these distributions look and what their mean and standard deviations are. Okay, so I'm going back to the notes. Okay, so here is a distribution of heights of 2-year-old males, and what we might do from this histogram is we might like to approximate. You see, to store this information takes a lot. It takes a lot of numbers, how high each bar is, what the cut points are. So there's kind of a lot of information in that histogram. Now I can approximate that histogram with a nice smooth normal curve of mean equal to whatever the mean in that underlying distribution is, and the standard deviation same. And we would be able to estimate all of the information in the gray rectangles by just looking at this one red curve. So in particular, I want to look at the curve. I just pasted this curve into Paint. So let me just go back and share my screen again. Okay, hopefully you can see the screen here. Okay, so if I wanted to estimate, I wanted to use the red curve to estimate the area of one of the gray rectangles. I can see the gray rectangle comes from here. Say this guy here, like so it's all. So the gray rectangle is this area I'm shading here in black. And I want to estimate that area by the area underneath the red curve. So I'll shade that here. Notice that part of the red shading overlaps with the gray, with the black shading, and part of it does not. In particular, the red shading overestimates in this upper left corner triangle, and then it underestimates here. So what happens in this situation is that the two different kinds of errors in estimation tend to cancel, so that the result is that the area under the normal curve is well estimated by the, let's get it. Suppose a random variable x is normally distributed with a mean sigma and a standard mean mu and a standard deviation sigma, then the area under the normal curve for any interval of values represents either the population, the proportion of the population with that characteristic, or the probability of randomly choosing a person from that population with that characteristic. All right, so the big question is, how do we find these areas? And we're going to work with the table. We're going to go to formulas and tables, and we'll pick that up in the next video. But the idea is that we would like to use the normal distribution to answer questions like, if last week's test had scores that were normally distributed with a mean of 80 and a standard deviation of 6, what percentage of scores were greater than 90? We would like to be able to answer that question. However, we're going to take a planned approach here. And we're going to first learn to calculate specified areas under the standard normal curve. And then once we have that down, we will learn to use a transformation to go from a standard normal, 0, 1, mean 0, standard deviation 1, and calculating probabilities on your standard normal curve. And we'll use this transformation here, z equals mu minus x minus mu over sigma, to get information about your general normal curve. Okay, so that transformation's in section 6.3. Section 6.2, we're going to learn all the skills of finding areas or probabilities associated with the standard normal. All right, so I will see you in the video for section 6.2.